So as you see here, this is on the canvas, and you're gonna see usually for each one of them, you're gonna have here two copies, right? One that doesn't end with C, the other one ends with dash C. Dash C is usually gonna be the colored one, like this one. You see this one, it's colored, so you're gonna see exactly what I'm working on. And the other one, if you like to see what you're gonna be looking at, I can just do this for quick. If you give me here a second, presentations is gonna be something like this. Difference is for each 8.5 by 11, like letter size, you're gonna see here two slides. So this is good actually for printing and putting notes if you like. And I have enough. I'm gonna see your slide set that's already posted, so you can print it if you like to. Some people prefers to write the pen and just put their notes next to it. Some people also prefer to use the colored one and put their notes here as we go. So you like just to type. So it's gonna be up to you guys. That's why I have two copies of one. I would urge you to download both of them and just keep it with you. And whenever you want to print maybe one, you can just use it. The one which is this one, I wouldn't urge you to print this. This is going to be destroying your cartridge or the toner or whatever that you're using in printing, unless you work for the government. So it should be a problem. Also, you're going to see that I put some homework. Did you guys see the homework I assigned already? Yes? No?
Yes.
So I'm gonna go here to assignment, and then you're gonna see here one homework is already assigned, right? And this homework, it should be simple. The first one should be very simple, right? Usually, beginning is usually simpler. And actually, it's about a kind of review here to the statics that you guys have taken in the past. So I put here three small problems about statics. And for each one of these problems, I'm gonna be asking you to do the reactions at the supports. So you have here three reactions. You have one in the y direction, one gonna be the x. This is what we call here a hinge, and this is what we call here a roller. So we call this simply supported structure or statically determined structure. So this shouldn't be a problem for you guys to find out the reactions. And it's gonna be also a good exercise and practice for you. And feel free to reach me, at the office hour to discuss it if you have trouble with this. In problem number 2 here, what I did, I start to make it a little bit complex, like you have uniform load and also you have point load at 6 feet, let's say from the right support. Total span is gonna be 30 feet as you see here, right? And for each one, again, I'm asking you to do the reactions at supports, right? So here you're gonna have your 3 reactions, and then draw the shear force diagram, and then also draw the bending moment diagram. When this is due, and this is gonna be like the norm for us, this is gonna be due midnight of Sunday. So it's gonna be January 31st, 11:59. Do you guys see this online? Can you please check it on Canvas? You see exactly what is
Yes.
they do and the time?
Yes.
So usually all my homework is gonna be due at the same time. So I'm gonna give you here a chance so that you can study over the weekend and finish your homework. Third problem is gonna be a simply supported beam with an overhang. This is what you call here a cantilever or an overhang. And as you see here, you have a point load and then you have uniform load, but not for the entire beam. This is gonna be for half of the beam span. So we call this from here to here, from A to B, we call this the span. The span means the distance from a support to a support, right? So the span here is gonna be 30 feet. The span here is gonna be 20 feet. And then the cantilever length is 10 feet. This is a part that sticks out, right? Why we call it cantilever? Because it sticks out and has a back span. So this part here we call the back span, and this give you the cantilever length. Okay. So for each one of them, you need to do the reactions, do the shear force diagram, do also the bending moment diagram. Any questions on that? Yes, I have a question here about will we be able to submit the homework as a PDF online? I'm gonna say yes, it's gonna be PDF online. So if you like, you can just write on a piece of paper, if this is your preference, and then scan it. Be sure that before you post it, that the scanning is good enough that once you put it on the screen, you're gonna be able to see it and read all the numbers. So be sure that it's legible, and then you can just upload it. If you like to do directly from your computer, you like to type it, it's gonna be up to you. I don't have any preference. It's gonna be up to you guys. What's important at the end, I need it to be an 8.5 by 11, is going to be scanned or in PDF format, and then you can post it through Canvas. Right, great. I'd like to go here with you through the course outline. Concrete as a material, we're going to be using it for our design. So what's going to happen? We need to study a little bit about the materials itself, about the concrete as a material. Concrete as a material is composed of a few components here. You're going to have cement, you're going to have aggregate, and then you're going to have water, and absolutely you're going to have a little bit of additives or admixtures. The reason that we have this admixtures is to enhance the properties of the concrete that you're casting. The reinforcing is not part of the concrete mix. You guys hear me about this? Reinforcement, you know, the reinforcing bars and whatever reinforcement that you put in the concrete, it is not part of the design mix. The design mix or the concrete mix that you're going to be using is composed of aggregate, cement, water. This gives you the three main components. When it comes to the aggregate, we have two types of aggregate. We have fine and coarse. I'm going to be going through this in details, just want to give you an idea. So this course here about design of reinforced concrete members. So first, I need to know what material I'm going to be using, what are the properties of these materials, strength, durability, and certain factors that I need to know about it. After that, I need to figure out the force that's going to be applied on the structural member. So for example, here is a beam. A beam is a structural member. Also, we have a column. We may have a column here supporting this beam, two columns. This is also a structural member. So you need to know exactly how much load you want this structure to support. This is why I'm asked here to figure out the reactions, the shear force diagram, and the bending moment diagram, because this is going to give you here the forces applied on the structural members. These forces you may call the demand. Demand means the forces that you want the structure to support. So we call this the demand. And then after that, you need to come up with the beam size or the column size, the amount of reinforcing that you're going to put there to figure out how much it's going to be able to support. So we call this the capacity. Ideal world, you'd like to have capacity more than the demand, or at least it's going to be equal to it. Does this make sense to everyone? Yes? No?
Yes.
Okay. So structural members, we have concrete beams, we have slabs, we have something that we call here a T-beam. Once we get to beams, you'll figure out what is this D-beam. We're going to have this doubly reinforced beams, which means reinforced is going to be on the top and the bottom of the beam. We're going to have also shearing beams. You guys understand the shear force, right? So the beam is going to be supporting bending moment and then shear. So all of that is going to be about bending moment, and then we're going to come here to shear. Now, after this, we're going to be talking about development splicers. What is that? You know, when you have bars, the bar usually it has a limited length. And in many cases, you'd like to splice a bar, meaning that you have a bar and the length is not enough, so you'd like to splice with another bar. So this is going to be about it, about this development with the splice of the rebar. After that, we're going to have, I'm going to skip this because this is related to it for now. So I'm going to say, what is this continuous construction? When you pour the concrete, you pour the beam with the concrete slab, or you pour the column separate from the beam. We're going to go into details about this. Now, in order for you to complete your design, you want to be sure that the deflection of the beam is not excessive. In many cases, the beam is strong enough to support the loads, but just again deform a lot. It's going to sag. You know, all of a sudden you look here in the roof or the framing right above you on the floor system, and then you see the beam is sagging, but it's strong enough. I mean, it's not collapsing. But because of the amount of deformation here, you're going to be hesitant to stay in this place. You're going to say, let me get out of here. I don't feel safe in this place. And for that reason, we need to do this serviceability checks, right? Serviceability means you want to be sure that the beam is not deflecting that much, you know? And then at a certain point, we need to know how to design concrete walls, columns, and footings. I guess by now you guys have seen the textbook. Any copy is going to be okay. Whatever I need out of this book, usually I have it in my slides. Having the book is good. You can read and see exactly how things are done into this book. From time to time, I go there and pick some problems from there. Also, we have the building code requirements. This is what you call here the ACI code. ACI is developed by the American Concrete Institute. This gave you the highest authority, let's say, in concrete business and concrete design and analysis and research. And the ACI, which is this American Concrete Institute, it has a committee, and the committee number is 318. So 318 is a committee number. So once you go there, you can look it up, building code requirements for structured concrete and commentary. This is going to be ACI 318. The dash 14, this is going to be the year. So they have versions. They have 10, and then they have 12. Now they have 14. So here's 14. This is the 14th version that we're going to be using. We have more references. We have this famous book by Park and Bowley, and this famous book is very good. It has some ideas. It has more explanation about concrete performance. However, just staying with the slide sets, the homework, and the project, you should be good. You should be in good shape. Some software we may need to use. We have something called PCA column. We have CSI column, and both of these two software, they're used for column design software to do the entire concrete section analysis for you. Also, we have this Etaps. I'm not sure if you guys heard about it or not. SAP 2000, lots of people. I'm sure that you guys start to use it. And it can do structure analysis for you. Also, it can do some concrete design or RAM structure system. If you have an access to any of these software, this is great. If not, we can have something about this. We can do something about it. Substitute with some other software and maybe some spreadsheets if you like to create one for your own. Grading policy. We have 10 for the homework, 10%. We're gonna have here course project is gonna be 15. So you have here 25%. So the work that you do here at home is gonna be 25%. The course project is kind of extension of the homework. So whenever that you have course project, it's gonna be the same as the homework. Let me explain this a little bit. As you understand, this is about here reinforced concrete design of members and stuff like this, right? So at a certain point, instead of just giving you here a separate homework by separate homework, I'm gonna put in here a building, like a sample building that we're gonna be doing analysis and design for it. And instead of assigning the homework as a separate, it's gonna be kind of continuous so that we continue and finish a complete building design. And with that, you feel that the homework here is interconnected to each other. And instead of having a separate homework by a separate homework, you're going to be looking here at the building, and then you're going to be start to look at the concrete slabs, and then beams within the same building, and then columns, and then foundation, and then walls of the same building. So you feel that you're taking this building here, and then you're building part by part. You're doing the design for it. So instead of having a homework, we're going to have a project. So we're going to have at the beginning a few homeworks, and then after that, we're going to be transferring all of our homework and our business into the course project, if this makes sense to you guys. First midterm, each midterm is going to be 25%, and your final also is going to be 25%. Now let's talk about concrete. We have, generally speaking, we have two types of concrete. We have plain concrete, and then we have also reinforced concrete. You're going to see also another homework on this little bit of introduction to concrete. Start from here all the way to the end. It's going to be very simple homework. And actually, if you start here to keep taking notes or trying to remember what I'm talking about, you'll figure out what is this about. I have a question here about the project, if it is done individually or with groups. This is going to be individually because it is like homework extension. So at the time when you have a project, I'm not going to assign a homework, if this makes sense. So it's going to be this or that. So as I said at the beginning, I'm going to have a few homeworks, and then after that, we're going to transfer it into the project. When it comes to concrete, we have plain concrete and reinforced concrete. What's the difference? I'm gonna say difference. Let's look here. Usually you can have like concrete slab on grade. We call this concrete slab on grade, and usually in many cases it's just done, made out of, it's just constructed out of plain concrete. There is no reinforcing. In many other cases, you're gonna see within the same concrete slab, you're gonna see some mesh. You're gonna see some reinforcing bars in both directions, right? And here's a beam, and you see here the reinforcing of the beam, right? Here's the concrete, and then here's the reinforcing. We call this longitudinal bars, if you like, and we call this ties. So this could be like a tie, right? It goes around the rebars and just tied together. So we call this reinforced concrete, we call this plain concrete when there is no reinforcing. But I want you here to look carefully at definition according to the code. It says here CBC. What is CBC? Anyone knows what's CBC?
California Building Code.
Yeah, what is IBC?
International Building Code.
Yeah, so let me type it. Right? This give you the CBC. IBC, International Building Code. So this give you the article number within the code, so that when you see it later on, you'll know what I'm talking about. This article 1901.2, it means chapter 19. So you need to know that this give you in chapter 19 of the CBC or IBC. So what is the IBC? What is the CBC? International Building Code is the mother of all construction building codes that we use. Let's say in the US and some other countries. What happened? California adopts the IBC with changes. So what happened? California, they have the commission for the code, construction code and business code when it comes to our business. And they have taken the IBC, converted into the CBC, and of course they have done some changes. So from time to time, when you see your CBC/IBC, you know which code I'm talking about. Now someone's gonna be confused and he's gonna say, you say CBC, IBC, so what is this? What is the IBC? What is the ACI? You call it also building code. The ACI is only related to concrete. So the CBC is not only for concrete design. The CBC, it is for all type of constructions. CBC includes concrete design, structure steel design, wood design, aluminum design, and lots of other issues. But the ACI is concerned only about reinforced concrete design. So what happened, the CBC or IBC includes chapter 19, right? And this chapter 19 is the ACI. So what is this ACI? ACI is actually chapter 19 of the IBC/CBC. So you go here to the CBC, you open chapter 19, and it just cross-reference the ACI 318/2014. This is exactly what it's doing. So you can either get this book, you can get maybe a PDF copy of it, or maybe printed copy. If you are planning to be in the construction business, or if you plan to be in the structure analysis business, you'd like to do concrete design, it's gonna be a good idea to have a copy of this book, of this code. So what it says here in plain concrete, it says it is concrete with no reinforcement. So if you have no reinforcement at all, you call plain concrete. Or you have little bit of reinforcing. What do I mean by this? It means that you put some reinforcing, but the amount of reinforcing is below the minimum required by the code. Which code? I'm going to say, of course, the ABC, the ACI, which is the same as the CBC. So let's say the code says in a beam like this, you need to have at least, let's say, 8 bars in this direction. And then you come here and then you just put a couple of bars. In this case, we're going to consider it to be plain concrete, not reinforced concrete. So in order for you to go to reinforced concrete, you need to have enough reinforcing according to the code. So I want you guys to be sure about this, because this is going to be one of the questions that you're going to see maybe in your midterm and also in your homework. When it comes to materials, as I said, that you're going to have aggregate and aggregate. We're going to have your fine aggregate, coarse aggregate, water. And of course, we need to have cement. So the cement we call cementitious material. Cementitious material here includes cement and other stuff, like fly ash. Gonna come to it. So when it comes to the cement, you can have here Portland cement, and Portland cement is the standard cement. The Portland cement complies with the ASTM C150. What is the ASTM? ASTM stands for American Standard for Testing and Materials. So if you like to call this whatever powder that you see, right, and you go there to purchase, let's say from some store, let's say from the Home Depot or whatever, right? If you like to call this a Portland cement, this material needs to comply with the ASTM C150. In this document, the ASTM C150, once you open it, you're going to see certain tests and certain physical properties and mechanical properties. And this is how you justify or determine that this material is a Portland cement. For example, what does it mean by steel material for you? You're going to say, what's the difference between steel and aluminum? For you, you're going to bring here two pieces. One is going to be aluminum, the other is going to be steel, right? And then how would you differentiate between the two? There is an ASTM number, let's say for the steel, like ASTM A615. Once you go through it, you're going to see the differences and the physical properties, mechanical properties, chemical properties. What testing can you do to prove or to confirm that this is real steel A615? Otherwise, you cannot really call it the steel. Same thing here with the Portland cement. So each one of these is going to be like a specification. We call this the ASTM specification, and this is what constitutes the Portland cement to be Portland cement. This is actually the very common cement that you're going to see everywhere, the Portland cement. And we have few types. We have, here's a cement, it comes in bags or it comes like loose, like this. We have very common type that we call here type 2. As it says here, general use, moderate sulfate resistant. And the other type, the famous type, is going to be also type 5. This is going to be the two common types that we use here. Let's say in Orange County, in LA County, in California. This is going to be the two common types that we use of the cement. Type 2 is common. This is going to be like the normal cement. We don't call it type 1. This is going to be type 2 that you use in construction and building anything out of concrete. Type 5 is going to be high sulfate resistant cement. Usually it is used in foundation whenever you have lots of sulfate in the ground. And also it is used whenever that you are close to the shore. So if you are close to the ocean, you'd like to do any construction, you cannot really use this type 2. It's not really strong enough for the chlorides and sulfates. So in this case, you're going to be switching to type 5. So again, we're going to have two common types, type 2 and type 5. This gave you the two common types that we use. The problem with cement that shrinks a lot, the amount of shrinkage that the cement is going to experience is high. This is the reason that from time to time, they're going to be adding some fly ash. You see this fly ash? And silica fume to substitute the cement. And instead of just adding lots of cement, you just add fly ash, you add silica fume, with that the shrink is going to be a little bit smaller, and it gives the same effect as a cement. Also, this kind of cheaper. So cheaper option to add a little bit of fly ash and silica fume, and this is called your cementitious material. You add to the cement in your concrete mix design. So what is the reason that we add fly ash and silica fume? So number one, reduce the cost of the concrete. Number two, to have less shrinkage. What's the problem with shrinkage? Just imagine here if you have this block of concrete and then shrinkage is going to happen. So the original size now wants to reduce. You're just going to see lots of cracks, like these cracks here. We call this shrinkage cracks. I'm sure that you guys, once you go here to any concrete slab and look at it, you're going to see lots of cracks. The reason that you have these cracks could be more than one different reason, right? Sometimes it's going to be just shrinkage cracks. Shrinkage cracks is going to be very small, and also we call it hair cracks. We may have also settlement cracks. So sometimes the part of the concrete slab is going to start to settle, and you're going to see some good cracks in there. And the crack can be all the way up to 1/4 of an inch when it comes to the width. But if you see here, very minor hair cracks, it doesn't mean that the concrete is collapsing. It just means that you have some shrinkage. And to work on this shrinkage cracks, it is usually preferable to put some reinforcing. So the reinforcing is going to keep the concrete in place. So if the concrete wants to shrink, it's going to see something there, which is the reinforcing, is going to be resisting this shrinkage. When it comes to the aggregate, we have two types of aggregate. We have the fine aggregate and the coarse aggregate. Here's the fine aggregate, which is the sand, and the coarse aggregate is going to be like the rock. And of course, they should comply with this STM C330 if you have lightweight concrete. Let me tell you a little bit about the lightweight concrete and normal weight concrete. In many cases, you'd like to reduce the weight of the building. And what's the importance of this? You know that any structural member is supposed to resist its own weight plus some additional load that goes on the top of it. Like, for example, if you have a beam or concrete slab, elevated slab. This slab is supporting its weight plus the weight of the components above it plus some life load. So you call it dead load and life load. What's the dead load? Dead load is going to be the weight of the structure itself, of the members, the steady components. And the life load is going to be the weight of the furniture, light equipment, the people, whatever that you add there that you can move around. If you like to reduce the dead load, in many cases, they said, why don't you switch to lighter rock? What does it mean by lighter rock? It means the density of the rock itself is going to be smaller than the density of the normal weight aggregate. So we have two types here of aggregate. We have normal weight aggregate, and then we have also lightweight aggregate. So actually it depends on the cost, on the weight. So you have many parameters. So it doesn't mean that lightweight is better than normal weight or normal weight is better than lightweight. It's just a decision which is going to be based on the use and the performance needed out of the concrete. So if you use here lighter aggregate, which means with lower unit weight or lower density, you're going to have lightweight concrete. If you use normal weight, you're going to have normal weight concrete. The sand is also the same thing. We have lightweight sand, and then we have also normal weight sand. So since we are talking here about the weight, we would like to figure out what is the density of the concrete, what is the unit weight of the concrete. So I'm going to jump here to the weight of the concrete. I'm going to say normal weight concrete. This is a number that you really need to know about and use in your analysis. This gamma, which is a unit weight, ranges from 145 to 150 pounds per cubic foot. Usually this number includes all the reinforcing in there. So if you take here a 1 cubic foot of concrete, it's going to weigh 150 PCF. So the number that you really would like to use is going to be this number. So if you're doing actual design, if you're doing a homework, just to say with this 150. So don't go to 145. But you're going to see some documents and some references, and from time to time you see maybe someone is doing an example and he's using 145. I'm going to say fine. But if you don't have any information, if it is not specified to you, please use this. Use 150 pounds per cubic foot. If you plan to use lightweight concrete, this is going to be the unit weight of the concrete, of the entire concrete here. It's going to be somewhere between 110 to 115 PCF. You see the difference? It's maybe about 25% to 30% difference. So it's going to be lighter. So what's happening here? In this case, use normal weight aggregate, and the unit weight of the aggregate itself is going to be 140 PCF. If you are able to change the aggregate to lightweight aggregate, unit weight of the aggregate itself is going to be 70 PCF, and therefore you're going to see here a drop from 150 to 115 or 110. Don't forget that this is going to be only the unit weight of the aggregate. Other components, we didn't change it. For example, the cement. We did not change the cement. Cement is going to be the same. There's not like normal weight cement and lightweight cement is going to be the same cement. This is why you see here the change from 140 to 70, like 1/2. What happened to the unit weight of the concrete? drop down maybe by 30%, from 150 to 110, or 25%, somewhere in there. Now, fine aggregate and coarse aggregate. It is very important that there is no organic materials within the sand or the rock, the coarse aggregate and the sand as an aggregate. You cannot have any organic materials with there. You cannot have any chlorides. Chlorides, very harmful when it comes to concrete. It destroyed the concrete and also corrode the reinforcing steel in there. Don't forget that you're going to have a concrete member. You're going to have lots of reinforcing in there. So once you have chlorides, it means it's going to be the end of the reinforcement. And also, it's harmful to the concrete itself as a material. Organic material is very dangerous because if you put some organic material within the mix, it's going to be causing segregation. It's going to be causing lots of cracks. Concrete is going to be just into pieces. So for example, if you bring a spoon of sugar and put in the concrete mix, and let's say the concrete mix size is about, let's say 3 or 4 cubic yards, there's not going to be any concrete. Concrete is going to be nothing. It's going to be loose. It's going to be just broken into pieces. So you don't do this. You try to clean the concrete, the aggregate, like the sand and the rock, before you bring it in. This is why we take samples of the aggregate and then we do testing before you start to mix the concrete and produce your concrete at the end. When it comes to the coarse aggregate, there is more restrictions, not just about having no organic materials, no chlorides. It's going to be also about the size of the aggregate. So let me confirm this with you. You see here the aggregate size? There's a maximum size that you can use. You cannot just go with any aggregate, because in some cases, the rock size is going to be too big, and you're going to have a problem here to fit it in the reinforcing. So if I go back here to this, just imagine that you have a good piece of rock, like a big size, and the width of this member is really small. So what's going to happen? This piece of rock is going to stuck between the 2 rebars, and then you're going to see some voids right below it when you pour the concrete. You don't want this to happen. This is why you're going to have something that we call the maximum aggregate size. What is the maximum aggregate size? The code has something to say about this. Here's the maximum or the nominal maximum aggregate size. What happened? The code says you have here 3 limits for the maximum size of the aggregate. I'm going to start here from the bottom. I'm going to say 3/4 of the minimum clear bar spacing. So let's say that you have 2 rebars. Here's one, here's the other one. The spacing between these 2 rebars, let's say 4 inches, right? Let's say the clear spacing is 4 inches. 3/4 of that is going to be 3/4 of the 4 inches, which means it's going to be 3 inches. So the maximum aggregate size in this case is going to be 3 inches. So if this distance, clear distance, is going to be 4 inches, your maximum aggregate size in this case is going to be 3 inches. So you're not going to have any problem. This piece of rock is not going to stuck between the 2 rebars. So you can pour the concrete easily. Also, if you are putting this aggregate or this concrete in a concrete slab, you know a concrete slab? The maximum aggregate size cannot be larger than 1/3 of the slab thickness. So what does it mean by that? Let's say the slab thickness is 8 inches. Divide this by 3. You're going to say 8 divided by 3 is going to be, let's say 2.8, 2.7 inches. This is going to be the maximum aggregate size. Also, it cannot be more than 1/5 of the smallest dimension between side of forms. So I'm going to go back here. If you don't mind, I'm going to go back to the same picture. Let's say here's one form is going to be in this side, one form is going to be in this side, you know, concrete form. And let's say the width here is 8 inches. So it says in a case like this, you cannot go to an aggregate size with anything greater than 1/5 of the 8 inch. So maybe 1.5 inch. So I'm going to say based on the 3 conditions, I'm going to go here with 1/5 of the smallest dimension. And this is going to be, let's say, about an inch, inch and a quarter. It is very standard that the size of the aggregate that we use, the maximum aggregate size, is 3/4 of an inch. Just keep this in mind. So the maximum aggregate size used in concrete is 3/4 of an inch. We have another size which is very common, which is 3/8 of an inch. They call this P gravel. So usually you'd like to use 3/4 of an inch. Otherwise, maybe you're going to be switching to 3/8 of an inch if the structural member is going to be very thin. To avoid any problems and to be sure that there's no voids inside the concrete after you pour the concrete, maybe you'd like to go to this P graph. We went through this concrete weight already. Now the water. You cannot just mix with any water. You need to be sure that the water is good for drinking. This is usually the test that they say. If you can drink it, it means it is good for concrete mix. But the code, of course, doesn't say that. But the code says it needs to be free of oils, any oils, metallic oils or organic oils. You cannot have any oils, acids, any organic materials. It needs to be clear of chlorides. Why? Because of steel. So you understand that. Also, you have this admixtures, which is additives to the concrete. Why do you add it? You add it because you'd like to enhance the performance of the concrete. During casting the concrete, which means during the construction process, and after. For example, we have this air entraining admixtures, this for workability. You know, there is a maximum amount of water that you can add to the concrete. And usually about 50% of the cement weight. Have you guys studied this before?
Yeah, we learned this in 377 lab.
Great, okay. I'm happy that some of you guys have taken it. So what happened, you have this maximum amount of water that you can add to the concrete, which is roughly about maybe 50%, maybe 45% of the cement weight. Now, the concrete is gonna be very stiff. So now you'd like to put it, and you need to have lots of vibration. It's gonna be very tough to set the concrete between forms and to cast it. So instead of adding more water, because water is gonna be reducing, I mean, the more water you add, the less strength you're gonna end up with the concrete. You're gonna be adding some air entraining admixtures to increase the workability of the concrete, just to make it easy to pour and compact within the forms. Also, you can add silica fume and fly ash. Why would you add this? To reduce shrinkage and provide the strength to the concrete, because like cementation material. You can also add this plasticizers for workability. So generally speaking, these admixtures, you add them to enhance the properties of the concrete, because you cannot gain this enhancement or this premium properties if you don't add these additives. It's gonna be just like cement and aggregate and water, and that's it. So if you like to enhance it, what do? You have an option of some admixtures that you can add. We have admixtures to make fast setting of the concrete. So if you want the concrete to harden very quickly and to gain high strength in a short time, there's an admixture for it. If you like the concrete to have delayed strength, so in many cases you have lots of heat produced from the chemical interaction between water and cement, and you like to delay this. You'd like to have low heat. So you have also special additive to delay the interaction between the water and the cement. And for that, you're not gonna gain the strength fast. So the strength is gonna take time, and the second is gonna take time before it happens for the concrete. So if you'd like to change any of this, the normal properties of the concrete, you just go and add some admixtures, which is very common. There is no actually mix without some admixtures and additives. It's very common. Concrete mix, as you see here, two different scales, right? This is something that you just do next to your house, right? You have a little bit of concrete mix. You can buy the bags ready-made. So actually, when you go to the Home Depot, you have ready-made bags. It has everything. It has a cement. It has a sand as an aggregate. It has a little bit also of this pea gravel. You can just buy it and use it. And what happens? You just mix it. You just mix it yourself, and then you can use it. This could be one of the ways. The other way is to buy it ready. So you go here to Batch Planet. You go to concrete mixer. And all what you need to do is to have just one concrete truck is going to be delivered to you. And then you can just use the concrete, which is very common. It depends on the size of work that you're planning to do. If you have a very small size, you can do something like this. If you like to purchase some concrete from a concrete supplier, this is what you need to do. You just ask me, say, I'd like to buy concrete with this strength. And then you figure out the strength. You tell them about the trends that you're looking for, and they're going to supply it to you. Now, talking about the strengths of the concrete properties, which is going to be the first thing when it comes to concrete design. It's going to be about the strengths of the concrete. We call the strengths of the concrete for the maximum stress that the spaceman is going to be able to handle. What do I mean by that? We bring a cylinder. The cylinder size is a standard. We have it either 6" for the diameter, 12" tall, or we may have 4" by 8". We put it in the machine and then we do the testing. And then we look for the maximum stress value that this cylinder is going to be able to attain. And this is going to be the maximum point. So here's the performance for one spaceman, another spaceman, third spaceman, fourth spaceman. So for example, for this spaceman here, it was able to reach 4,000 psi, which is 4 KSI. We'll call it 4,000 psi concrete. This is the way that we call it. With that, I'm going to stop here, and please feel free to ask me any questions. If you like to see me at the office hour, feel free to move to it now. And please sign out. Go ahead and type your name. If you have any questions, you can stay here with me, or we can just meet at the office hour.
Thank you, Professor.